let's get started. Okay. So I was in the middle of this technical but rather useful result, and let's recall the background. The background is, well, we're considering the Euler equations, the equations for axisymmetric flow with us. Where are the Euler equations? Here they are. They're these basic conserved quantities. And so essentially we're asking, suppose we know we have information about the energy and this. So for example, the L infinity norm of this quantity and these quantities. So all of these are preserved by the flow. Are there certain kinds of information about those quantities that allow us, that give us a lot of sort of structural conditions on the vorticity? Okay, that's the question. And so the lemma we're proving says yes, that is true. Okay, so first we derive formulas for the sort of the analog of the Biot-Savart kernel in this axisymmetric setting. And so here's the lemma we're proving. And so we exactly assume things about these conserved quantities. Here they are. And so the first ones are just normalizations. We assume bounds on the L infinity norm. The kind of bounds that are preserved by the flow. And we assume the energy, the last condition is that the energy is close to maximal given the other conditions. And the conclusion is that there exists some point x star such that the vorticity concentrates around x star. So for example, if I take capital R, epsilon to the -1/2, this would say that in a ball of radius square root of epsilon around the point x star, all but 1 over log epsilon, or constant over log epsilon, vorticity is found within that ball. And this shouldn't be here. So I think last time I was writing I was showing the dependence of the constants on this parameter lambda. I've stopped doing that because it's not that useful. Okay, so and so we're in the middle of this. It's kind of long and technical thing. And so what did we do so far? We showed that the energy is defined in terms of this sort of opaque kernel, the axisymmetric reduction of the Green's function on R3. And so we related that to a more comprehensible looking thing, which is this energy E1, which just looks like this. So it's like the standard Green's function on R3. And then there are weights coming from the axisymmetric setting here. And okay, I've said that the distance from x prime is less than or equal to 1, and so then this plus is redundant. This is the positive part of the log, but it'll always be positive in this case. Okay, and so then essentially the idea was that if we take this identity, this inequality, this E1 is less than, E1 is bigger than 1/2 log epsilon, and we subtract from both sides, essentially log epsilon times the square root of RR prime times the integral, and we subtract a certain constant from both sides, then we can rewrite this identity. I didn't do it quite like this, but we can rewrite the identity, the estimate in this form, and maybe there's a C. I think I'm missing a constant someplace. Okay, and so we introduced this function capital F, or little f rather. And this function has the property that this function is telling me, so we have this inequality that says that f is greater than or equal to 0. So square root of r prime is less than or equal to 1/2 plus 1/4 r squared is round trip. And this tells us how close we are to achieving equality in there. And so we know that in fact equality is achieved only when r and r prime are equal to 1. And so if we can prove upper bounds for this integral to f, then that says that omega is concentrating near near the minimum of f, which is where r and r prime are equal to 1. Okay, And so then that's, again, we didn't quite phrase it in this way, but this was say half of the main idea. Let me see. Right. And so, so then we proved an upper bound for the right-hand side. And so the main step was the one exhibited here. If we fix R, then we, and so here's this point at which we use the assumption that the L infinity norm is bounded above by 1 over pi epsilon squared. Okay, that's what gives the upper bound on the energy. And the point is, I guess, if I look up here, you know, if I didn't have these things, if these were just 1, then this would be a situation we already understand. This would be the Green's function on R2, and we already proved vorticity concentration estimates for that in that setting. And so the problem is that we have this weight here, and so what we're aiming for is to show that, in fact, where the vorticity is concentrated, the square root of R prime is basically 1. And so we can, and then we've reduced ourselves to the previous situation, and we can argue as before. This is in some way the idea. And the way we do this is, again, by rewriting S here and then proving an upper bound for the right-hand side, which will tell us that omega is concentrated near a, so this will say that the integral of f against omega of x prime is bounded by, the right-hand side is going to end up being bounded by a constant. So the integral of f will be bounded by a constant over log epsilon, small. And this says that omega then is concentrated near the minimum of f, where the radius is roughly 1. Okay, so this was the idea. There's one other idea, which was to say that if I look outside the ball of, if I look on the complement here, what do we have? Here we have, so on the one hand, we have a lower bound for the integral of, for the energy over all of the half plane. And then we have an upper bound near the diagonal. And by subtracting these, we get a lower bound away from the diagonal. And also we know that away from the diagonal, we know that this log epsilon over x minus x prime, we know that that's less than or equal to log epsilon over r epsilon, which is minus log r. Okay, and so the other idea is to say we have a lower bound away from the diagonal. We can just have a pointwise estimate for this epsilon over x minus x prime. This log is again bounded by minus log r, and then we divide both sides by that. And okay, and so that's that. And so here, so finally we arrived at, this is the point we arrived at the end of the hour. We got to here. And so the great thing here is that okay, so what do we, so we have one term, oops. We have this term. This tells us that the integral of f is small, and so again, we're concentrating near where where r is equal to 1. And then here we have an integral away from the diagonal of omega prime. And so this is really the setting, yeah, well, this is really telling us that, okay, the away from the diagonal, there's not much stuff. And that's what we want. We want to show that the vorticity is concentrated near where x is equal to x prime. Okay, and so then quickly, looking at this inequality, we we can think of this as being, let's write it as the integral of h and then a dx prime. Okay, so if I look at the integral, so I know the integral of omega dx is equal to 1, and so I look at the inner things as a function of omega. This has to be small some of the time for some omega, just by something like Chebyshev's inequality. And so, so if when I average over x, this quantity is small, then it's got to be small for some particular choices of x. And that's the second inequality. Okay, and then for this x, well, so on the one hand, we have an upper bound for this. So, yeah, an upper bound for this. So the integral over points x prime who are outside the ball radius r epsilon around x is small. And that tells us that the integral of points inside the ball, we know the total integral of omega is 1. Therefore, the integral of omega within the ball is close to 1. Okay, good. And so we found a ball with where the vorticity is concentrated. And also, we know that the integral of this is small. And that tells us that there's got to be some point x prime where omega is positive, where this is the case. Okay, so something on the support of omega. And we saw that, that there's just a pointwise inequality, which says that this the only way this can happen is if both r and r prime, in fact, are close to 1, close to the minimum value. Okay, and so from this inequality 4, we get all the conclusions we want. We say that we have vorticity concentration, and we have vorticity concentration around a point where the r component is close to 1. Okay, so there'll be detailed proof of this in notes that I'll post online eventually, but we've gone through essentially all the details. Okay, good. And so, so that was the most technical part of the present discussion. What I want to do next is to discuss the following theorem. And here it is. And so there's a broken link here, a broken reference. What I want is to consider a solution of the Euler equation for initial data who satisfies all of these conditions. So I assume this about the initial data. So this question mark, this should be a 2. Okay, and so the conditions, you know, the integral of omega is equal to 1, the integral of omega r squared is equal to 1. The conditions that we have just shown imply that the vorticity is concentrated around some point where the radial coordinate r is very close to 1, when epsilon is small. Okay, and we also know that those conditions are all preserved by the flow, and so then at every subsequent time for the solution of the Euler equation, the vorticity concentrated around a point, et cetera, et cetera. Okay, good. So then and so I should have said well, postness for the equation is known to hold under for initial velocity, for initial vorticity in L infinity. And so L infinity and L1, which is the case we're considering here. Okay, and so so a solution exists. And so the conclusion is, well, the first part of the conclusion are just things that exactly follow from the conservation of all the conserved quantities, energy and so on, and the previous lemma. So we made this hypothesis times 0. They continue to hold at later times, and according to the previous lemma, they imply that for every epsilon and for every tau, so for every epsilon, I have a different solution, but these statements apply uniformly to epsilons and in particular for epsilon small. For every epsilon, for every tau, there exists a x star epsilon at time tau. We can think of this as being, you know, roughly the center of vorticity. And what do we know? We know its r component is close to 1. And we know that the vorticity concentrates around this point. And so if I look, and so the total vorticity is 1. If I look in a ball of radius r epsilon around this point x star epsilon, then I will find all but constant over log r of the vorticity. And so again, I was writing of capital R as being epsilon to the minus 1/2. In a ball of square epsilon around my point, I have all but 1 over log epsilon of the vorticity. Okay, and so so the first conclusions follow immediately from things we've said so far. The only new part is this one. And so this tells us how, and so a picture is, we have the, let's draw a picture here. We have the RZ plane, and we have some, let's say here's R's 1. We have some initial blob of vorticity, which is near here. And this says that as time evolves, it moves upward. Well, as I've, the direction, actually I should check, but I should check the sign. But if I've gotten the sign right, it moves upward. In other words, the Z component at time tau differs from the Z component at time 0 by this factor, which is linear in tau. So the velocity is 1 over 4 pi tau. This is the only new assertion. And let me see. So note an important thing. And so here I had to rescale the time variable. So tau is a rescale time variable. We'll see in a second why this is needed. And so what this says is that in the original time variable, the velocity is order log epsilon. So if at time, if tau is 1, then t is 1 over log epsilon. That's how long it takes to travel distances of order 1. And so once I and so the claim is once I rescale in time, we have this velocity is independent of epsilon, or if I don't rescale, the velocity is a logarithmic epsilon. Okay, and so I'm going to try to prove this, and we'll focus on the idea first. And so the first, let's say my first goal will be to understand where this log epsilon factor comes from. Well, and how can I capture this quantity? So I want to figure out how the center of vorticity is moving. For some reason, I have the theorem twice. I think the first statement is the better one. Let me make a remark. So here's a remark. In the statement of the theorem, I said for every epsilon there exists an x star such that this concentration inequality holds for every r between 1 and 1 over epsilon. What I actually proved is that for every capital R, there exists a point x star, say, but that point may depend on capital R. So it may be that if I want to find concentration on a certain scale, I get 1 point. On a different scale, I'll get a slightly different point. And so there's a final step which I didn't do, which just involves messing around to get this last improvement of this statement. And so I might start with a small choice of R, just big enough to contain, say, half the vorticity. And then if I take any other, if I take a larger R, well, the ball around there is still going to should contain more than half the vorticity. So those two balls will intersect, and then I can say that the two centers are kind of close. And just by messing around in this way and changing the constants a bit, I can get a uniform R. And so I can get I can get an x star such that this inequality holds for all capital R. And here I have the what we found before was actually the 1 over log capital R. But this says we can take capital R d epsilon in that inequality. Okay, so so there's some stuff I skipped in the proof of this theorem. Some just technical messing around the last stage. Okay, and that appears right. I wrote the improved form here, and so here I'm relying on the stuff I didn't prove. Okay, so now let's get to work. Geez. So how to, let's, it's better, how to capture the motion of, so let's say, So one, is it the existence? I said this before, let's write down the existence of x star epsilon of tau satisfying 7 and 8 follows directly from the lemma and the conservation laws. And the assumptions on the data. On the data. And so we just have to ask how to capture the motion of x star epsilon of tau. You know, I shouldn't write these subscript stars because I just make or x epsilon star. I just make a unreadable mess. And so I'll just write x epsilon without the subscript. The unreadable mess. Okay, and so here's what I want to do. I'll define. So what I want to do is I want to look at. I'll look at the integral over the half space of, say, phi times omega epsilon of x tau dx for a test function phi. Okay, and so I'm interested in how this point x star moves. And I know the r component is always about equal to 1. It's 1 plus or minus a constant over log epsilon. So I only care about the z component. And I know it's, you know, staying in this line. I sort of know it's just moving up and down around a track, along the track. And so so let's design a test function that tells us where it is with respect to the z variable. Let's say phi of r and z will be f of r times g of z. Let's say I want it to be C2 with compact support in the half plane. And so f of r will look like this. Say, I don't know what, here's 1. I want it to be 1 in a neighborhood of 1 and have compact support. I think I said 1/3 and 3 and 2/3 and 3/2. Okay, so anyway, it looks like that. And so its support is in the interval from 1/3 to 3, and it's equal to 1 in the interval from 2/3 to 3/2. Nothing special about these numbers. I just want it to be 1 near where r, because I know that the vorticity, I know that this is always concentrated near r equals 1. So this and g of z, let's write this down. Instead of drawing a picture, g of z will equal, well, I want this to tell me how far I've moved from the initial position. And so there's some z epsilon of 0. If Okay, so again, it starts out at a certain height. There's some z epsilon of 0. And I want to know how far it moves in the vertical direction from there. And so, but I need compact support. And so let's say for now, I'm only interested in interval of length 2 centered at this point, and 0 if this is bigger than 2, and it will look like this. Okay, and so as long as I haven't moved too far from my initial position, this will tell me what the new position is. It'll tell me how far I moved. Okay, and so I'd like to claim that the integral of this phi omega epsilon dr dz is z epsilon. Hold on, I want a tau here. Well, and then there's an error. The error should be something like, let's say, log epsilon to the -1, as long as and epsilon is sufficiently small. So what do I mean by sufficiently small? What I mean is, well, let's see, here's a picture of the RZ plane. And we have this function phi. So here's, let's say, R is 1 here. And the support of phi might look like this. And then we have the smaller region where phi is z minus z epsilon of 0. And this is centered around r equals 1. Okay, and what I know is that I know there's this sort of approximate center of vorticity at this point x. I know that for every tau, there's an x star epsilon tau. And I know that if epsilon is small enough, then I know that if epsilon is small enough, then I'm left-handed, and I think this iPad is designed so that if I rest my hand on the iPad, then I'm likely to hit something that I think it's designed so that if you're right-handed and you rest your hand on the iPad, you don't do anything unexpected. And so by default, if you're left-handed, then things can happen. Okay, so so if epsilon is small enough, then r epsilon of tau minus 1 is less than whatever it is, 1/3. And so the center of vorticity lies within this region where this function f is equal to 1. Okay, that's the smallest condition. And we know that this r epsilon tau minus 1 is bounded by like a square log epsilon of the -1/2 maybe. So it goes to 0, so epsilon goes to 0. Okay, and so here's the proof. Well, the integral of phi omega epsilon dr dz is, I want to integrate over the ball of radius, say, square of epsilon around the point x star of tau. And then I want to integrate over the complement. Oops, it's x epsilon of tau. And phi omega epsilon dr dz. Let's see. Okay, and so in the ball of radius squared of epsilon of x epsilon of tau, we know that phi of x is phi the center. Plus something that's bounded by the Lipschitz norm, which is the, say the C1 norm of phi times the radius of the ball. And this is just a constant, so we'll just write this as the, a constant. In other words, it's independent of epsilon. Okay, and so, and the integral over this ball of radius squared of epsilon of omega is at least 1 minus constant over log epsilon minus 1/2, which is log 1 over epsilon. It's this. So if I then look at the first contribution, so if I look at this, I'm integrating a function which is basically constant, up to square root of epsilon, and the integral over the ball is 1 minus this, and so my conclusion is the integral. Let's see. In fact, I know the total integral of omega is 1. So the integral of this ball it will be phi at the center minus a constant over log epsilon. If you just do the arithmetic, so there are two sources of errors. They're the errors from this and from that, and these ones are negligible compared to the other ones. Or let's say plus big O of okay, and so and if equals g of remember phi is the product of f and g. F is 1 because we've arranged that the R component is in this strip, and so this is g of z epsilon of tau plus the error terms, and this is z epsilon of tau minus z epsilon of 0 plus the error terms. Okay, so we can detect the height by integrating as a suitable test function. And so now our target is now our goal is to understand say d, the tau derivative of this phi and omega epsilon. Okay, and that's what I want to do. Okay. And so for this, we have to recall the equation. And so the equation is Okay, so we have the Euler equations. Let's they're up here, I guess. Here they are. So we have the equations which I've written in sort of a divergence form, and so this I've carried this divergence aside. If I want to get an equation for the vorticity, I just apply the orthogonal gradient to this thing, and it'll knock out the pressure term, and it'll convert, and so the orthogonal gradient of d tau u is d tau of the orthogonal gradient of u, which is the orthogonal divergence, which is d tau of the vorticity. And then I'll just write this, well, I'll just write it like this. So we have a log epsilon having, and so we'll see in a second why this is necessary. If I hadn't put this here, I would have realized I have to do it. This is not a. Okay, that's the equation. And so let's multiply by, that's one way of writing the equation. So let's keep this out here for now. Okay, so I can, things are smooth enough. I can exchange integration and differentiation. I can bring the integral under the derivative under the integral sign. And so then I'll have phi epsilon times d tau omega epsilon. That's phi times grad perp 1 over r divergence of r u tensor u. And maybe there's a minus sign. Dx. And phi is compact to support, so I can integrate by parts to my heart's content. And so the first time I integrate by parts, I'll get a so this is phi times well, okay, let me just write it. So here I have you know, a 2 by 2 matrix. When I take the first divergence, I get a vector with 2 components, and I take the second orthogonal divergence, I get a scalar. And so this is the product of 2 scalars. Here when I integrate by parts, I'll first get a so grad perp phi, the dot product with these things. I'll have a dot product of 2 vectors. And then when I integrate by parts again, I'll have I'll get a matrix of derivatives of phi. Well, let's write it down. So I'll have, I'm going to end up integrating by parts twice. And so each time I get a minus sign, in the end, I'll have 2 minus signs. So I'll have grad perp phi over r. That's the first integration by parts. And then I bring the 1 over r here, then integrate by parts again. And I'm left with u tensor u times r, and dx is dr dz. Okay, simple. And it's useful to break this into 2 pieces. And so one will be a, and so we may write this out in components later on, but well, let's do this now. So if I differentiate the phi, I'll have the gradient of the orthogonal gradient of phi, the Hilbert-Schmidt inner product with u tensor u, and then the 1 over r will cancel the 1 over r, and I'll have this. And then I'll also have a term where I have where I have r gradient of 1 over r. And then really okay, we have all of this. So here's what we get. Okay, and so I claim that I want to justify the log epsilon scaling. So remember, this is telling me how this quantity, who I'm looking at, is telling me how does the vortex move. And so the right scaling is the one in which this tau derivative will be of order 1. So that will be the one in which the velocity is order 1. And so let's I'm going to and what this quantity up here is it's the directional derivative. It's u dot gradient of 1 over r times r. So that's a scalar, and u dot grad perp phi. And this too is divided by log epsilon. Okay, and let's, I want to make this smaller so I can carry it around with me. Well, let's do this. Okay, let's worry about that later. Okay, and so here's the point. The point is, how big is the L2 norm of u? Do we remember that? I should have emphasized this, but how big is the L2 norm of u? How big is the energy? That's what we have to ask ourselves. Because what we see here are things involving basically these can be controlled by the L2 norm of u. This is quadratic in u. This too is quadratic in u. I've written in a way that describes it, that conceals that. But the point is that the integral of r u squared dr dz over the half plane is like 1/2 log epsilon plus a bounded term. Okay, and here again, there's something I didn't say as clearly as I should have. And so what we talked about at gradient was the lower bound. So we in fact, we assumed the energy lower bound. And we prove these consequences. In the previous lemma, if we looked at it more carefully, we would have seen that in fact, implicit in the proof is an upper bound, saying that not only by assumption the energy is not much less than is log epsilon over 2 minus the constant. In fact, it can also be once we have these other assumptions, the energy can be no greater than log epsilon over 2 plus a constant. Okay, so that's the energy. And so in other words, if I want to see the energy be of order 1, I need to divide it by log epsilon. And that's exactly what I've done here. I've taken, so this is a quantity whose integral is bounded. And so this d tau phi omega epsilon okay, so this first term is just a combination. It's a linear combination of second derivatives, phi xi, phi xj, or phi r, phi z, second derivatives, multiplied by quantities involving components of u, ui, uj. And so that's bounded by a constant times the C2 norm of phi, the supernorm of all the second derivatives, times u squared over, and let me put an r here and a 1 over r there. But 1 over r is always at most almost 3 on the support of phi. And so, right, and so I want a u squared times r. And I want to divide by log epsilon. Dr dz. Right. So let me remark also, this was the, so we wrote this is the same thing as the energy of omega. We proved this a while ago. And so when we stated this bound for the energy as being of order log epsilon over 2, we stated in terms of the energy of omega rather than the Elton norm view, but they're the same thing. Okay, and so this is then less than a constant. That depends on phi, but oops, there's only one term. The second term has the same character. So there are terms involving derivatives of r, a fixed function, derivatives of phi, a fixed function, and quadratic terms in u. And so these other terms have the form phi c1. And again, I should divide by r someplace. So I would have a u squared over ui times uj over r, and I would have r squared in the numerator. Sorry, I guess I have the r here. That's okay. Times u squared r over log epsilon dr dz, which is bounded by a constant c. Okay, and so so what we've seen so far is just that in order to control the velocity, I need to rescale by this logarithmic factor. It's possible I've done sloppy estimates, and in fact, the velocities are the left-hand side is smaller than that. But we'll see. No, this is really correct. Okay, and so what we'll do now is we'll examine this. So the program is we have this identity. We have this identity, and we want to just examine that and understand the right-hand side in order to see how the left-hand side is changing. To get to understand the left side, and so what do we know? We know that at every time there's this center vortex. We know there's this blob, this ball of radius. We know there's this point around which the vortex is concentrated, and we know the Biot-Savart law, which allows us to reconstruct the velocity u from the vorticity. And so our goal then is to, and so what we'll see is, well, I guess I'll talk about this next time. But the first thing we can see is that so the test function phi is linear in this region, right? In this central square, in the central rectangle, the test function phi is linear, and therefore the second derivatives vanish in that region. And so this first integral is supported away from the center of vorticity. And so if we can show, for example, that the L2 norm of u is so we know the L2 norm is divergent. I mean, we know that u squared over log epsilon is order 1. If we can show that L2 norm is concentrated near the center of vorticity, then in fact the first term, don't have to worry about it. It's not there. And then if we can understand, we'll look at this in more detail and see what do we need to do to. So what we want is for the right-hand side to be to give us this constant upward velocity in the z direction with a factor of 1 over 4 pi. And the program is, again, we know something about the vorticity concentration. We can then use the Biot-Savart law in this framework to reconstruct the velocity u, and then we can use that to understand the right-hand side. Okay, so I'm not sure how much detail we'll do this in. It's conceptually it's pretty clear, but then there's just a lot of calculations. And I feel like we may have been overdoing it on the technicalities recently. And so if you have preferences for seeing all or some or none of the detailed computations, then feel free to let me know. Okay, that's it for today. And I'll see you all tomorrow. And also I can hang around for 10 or 15 minutes, say 10 minutes for questions if you have any. And so we'll start tomorrow with this. And we'll begin looking at what we need. So here I'm following a paper of Benedetto, Cagliotto, and Marchioro from 2002, Cagliotti and Marchioro from 2002. I believe they didn't do this last step this way. And so the vorticity concentration part, I took their proof and I rewrote it to make it easier for me to understand, because the original proof was I would say even worse than the one I presented here. And in terms of exposition, nice ideas, smart ideas. And I think that they do the second half, this controlling the motion, in a different way. So they don't, I think they look more at the point-wise computations, but I didn't look at it very carefully because this is the way I like to do it. Okay. Let's see. So I see there are the go slower and go faster buttons here in the chat. Okay. All right. Okay, I'm going to stop the recording. So you can now ask a question without your voice being recorded if you have questions. And there seems to be something. Yes, the question is, am I still going to post notes on my webpage? The answer is yes. I'm just a bit behind, but yeah, I will assume. Yes. Right, I should get caught up before the weekend because next week is going to be a bit busy for me with this workshop. Okay. Let's stop the sharing.
Hi, if I'm not late, I will ask a question. Hi, and regarding the Lake equation. So if you had put a weight that is not like say R, like for the axisymmetric Euler, but you put like a more generic weight, and then you said that you have like the extra conserved quantity of say in the case of radial weights, for example. And then I was wondering, like how much so this approach basically could not be easily implemented, as I say, to track the, say, vorticity concentration, since this conserved quantity is missing. And then also, say, the second point would be, if one chooses the weight carefully, then these kind of computations where you need the weight R, like the very last one you did, this could still work, no?
Yeah, actually, there's going to be talk about this next week in the workshop. about exactly this issue of vortex dynamics for the general Lake equations. But here's the idea. Let me see. Okay, so what happens with Euler equations is that there's this vortex, there's a weight r, and the vortex moves along level such the weight r, just the weight, so it just stays a constant distance from the z-axis. So for the general Lake equation, if you have a single vortex, the theorem is that, and this is the theorem of de Keyser and Van Schaftingen will speak next week on this. The theorem is that the vortex moves along a level set of the weight b.
Okay.
This is kind of natural because as long as the vortex is concentrated, there's this the energy is really concentrated around the vortex location, and so and it has a weight. This is rather natural in some ways. And so, what can you do? What you need is to say, so the argument is something like, as long as the vortex is where it should be, where the weight is equal to b, then the hypothesis, then there's some kind of concentration inequality like the one that we proved. It's in fact, he has a very elegant proof there. But as long as the vortex is where it should be, then it's got to be kind of concentrated, because what do? You take initial data with so the vortex location and this and these conserved quantities imply concentration on a certain scale, and as long as it's where it should be, then those conditions are true, and then you can control the vortex motion. And so the idea is that, so suppose it deviates a bit from where it should be, from this line of constant b. Then you, as that happens, you lose control over the vorticity concentration, and you lose control over the velocity, because you need, so once you know it's concentrated, you can compute the velocities and do the stuff that I'll do tomorrow. And so the idea is eventually there's a kind of inequality saying that so there are these two quantities: the deviation of the vortex from where it should be, and the deviation of the velocity field from what it should be. And if you can control the deviation of the velocity field by the deviation of vorticity, then essentially this is a kind of Grunwald inequality argument. That and so that may not have been terribly open, but that's the idea. And you can see the talk next week, and so he'll do in an hour. When I'm doing it very slowly in many hours, but the same ingredients will be there.
Thank you.
You're welcome.